Cement is a finely powdered substance that acts as a binding agent, setting and hardening to adhere to building units such as stones, tiles, and bricks. So the main composition of cement includes limestone, sand or clay. Limestone is the source for calcium, sand is the source for silicon, and then we have bauxite, which is the source for aluminium, and then we have iron ore. And the classification of cement is primarily the hydraulic cement and the non-hydraulic cement. The hydraulic cement, such as the Portland cement, sets and hardens through hydration reactions with water. Okay, while the non-hydraulic cement sets and hardens through carbonation reactions with carbon dioxide in the air. Cement basically constitutes of two different types of compounds. We have the argillaceous compound, which is clay, and the calcareous compound, which is lime. And these are the raw materials for present in cement. So we have lime, we have silica, we have alumina, we have gypsum, which is usually added towards the end of the manufacturing process to control certain time. So we have iron oxide, we have some percentages of magnesia, sulfur, and alkali. As you can see, these are the percentage compositions. So we'll be looking at these different raw materials, we'll be looking at the functions of these raw materials in cement. Let's take a look at lime. The lime itself, calcium oxide, impacts strength and soundness. Soundness we mean here is change in volume to the cement. So if it is in excess, it makes the cement unsound and causes it to expand and disintegrate. All right. So but if it is deficient, it reduces the strength of the cement and causes it to set quickly, and we don't want that. So let's take a look at silica. Silica also imparts strength to the cement, but if it is in excess, it increases the strength of the cement, but also increases the setting time. So we don't really want that. So, and then we have the alumina. The alumina imparts quick setting properties. It allows for quick setting. And then if it is in excess, it weakens the cement. All right. And the alumina actually act as flux and help in reducing the clinkering temperature during the burning of the cement. Then we have the gypsum. The gypsum actually helps in increasing the initial setting time of the cement, and it prevents what we know as flash set. All right. Then we have the iron oxide. Basically, it imparts color, and it does impart strength, hardness, toughness to the cement. And talking about color, it imparts a reddish brown tint in the cement. So we have the other components such as the magnesia. It imparts color too and hardness. Magnesia does that. Then sulfur is responsible for inducing the soundness in the cement, while we have some little percentage of alkali. The presence of alkalis in cement actually leads to a fluorescence and staining of the structure in which the cement is used for construction. So a fluorescence, the ability for alkali to absorb moisture and react with it, okay, and leads to the development of white gray spots over the surface of the structure. So we'll be looking at the types of cement. So we have the rapid hardening cement, we have the extra rapid hardening cement, we have a quick setting cement, a sulfate resistant cement, we have a super sulfate cement, we have a Portland slag cement, We have Portland pozzolana cement. We also have lastly the ordinary Portland cement. So the ordinary Portland cement is what we'll be considering, and it is the most commonly used type of cement. Actually, it is suitable for general construction work. So in the manufacture of Portland cement, as we'll be considering, cement is actually made by heating limestone. Limestone is calcium carbonate, okay? It is made by heating limestone with small quantities of other materials associated with it, such as clay, at temperatures of 1450 degrees Celsius in a rotary kiln. The kiln is the reactor where the cement materials are being heated, all right? And the process that is being undergone in the rotary kiln is called calcination, and we'll be discussing that in the later end. So in calcination, a molecule of carbon dioxide is liberated from the calcium carbonate to form calcium oxide, which we call lime or quicklime. Then this is then blended with other materials that have been included in the mix. Now, the resulting hard substance from the kiln is called the clinker. The clinker is then ground with a small amount of gypsum. The gypsum helps to control the setting time. So it's ground into powder to make ordinary Portland cement, okay, which we say is the most commonly used cement for general construction work. So let's look at this flow chart for the manufacture of Portland cement. I just gave a little introduction about that. So you could see step 1 here. What is actually happening here is the quarrying limestone, which is a cement rock such as clay or shell. They are being quarried, broken down and brought to the cement works. And these rocks actually contains lime, calcium trisulcarbonate 4, and it contains silica, which is actually sand, silicon dioxide. It contains alumina, all right. It contains some ferrous oxide. So, and these are the raw materials for the cement manufacture. Then if you look at the step 2 here, what is happening here is that the raw materials are being prepared, all right, or homogenized to form a consistent product. And it is essential that the same mixture of minerals is used every time. And it's for this reason that the exact composition of the limestone and the clay is determined at this point. So there are several tests that have been taken or subjected to these materials in where they call the lab section. They carry out some tests to actually determine the composition of some of these materials. So then the rock is ground into fine particles to increase the efficiency. So in stage 2, you could see a raw mill. So these whole materials are being ground to increase the efficiency of the reaction in the raw mill. And usually there are 2 different processes at this stage. We have the dry process and we have the wet process. But for the manufacture of Portland cement, we employ the dry process. Water is not involved. So in step 3, you could see here is the clinkering. Here the raw materials, if you look closely before step 3, there's some dust separation and all of that, and some preheating. So in step 3, the raw materials are dried, heated, and fed into a rotary kiln. All right, they are dried, heated, and fed into a rotary kiln where they are heated. All right. So, and in the rotary kiln, the raw materials react. All right, the whole raw material, the alumina, the silica, the iron oxide, they all react at very high temperatures to form tricalcium silicates, all right, which we call C3S. And then we have the dicalcium silicates, which is the C2S. We have tricalcium aluminate. This is also formed, which we call C3A. Then we have the tetracalcium aluminoferrate, which we call the C4AF. All right. So these are some of the materials that are being formed in the process of heating in the kiln. So the kiln is actually a big sort of cylindrical shell of about 60 meters long, made of steel. So inside of it, if you look at this illustration here, you could see how the internal structure looks like. And in the kiln is divided into several zones of heating. Then if you look at the flow chart here, you can see I've just indicated zone 1, zone 2, zone 3, zone 4. So in zone 1, this is where decarbonation happens. Remember, the cement is made up of calcium tricarbonate. It has a higher percentage of calcium tricarbonate. And in the zone 1, there is the formation of C3A, okay, above 900 degrees Celsius. So basically what happens in zone 1 is that decarbonation, okay, whereby calcium tricarbonate 4 is being heated as it disintegrates into lime, quick lime, and calcium oxide is released. So in zone 2, exothermic reactions and the formation of secondary silicate phases, gets to show up, whereby the lime that has been formed in zone 1 reacts with more silica. All right. So once that is completed, at high temperatures between 1100 and 1300. So what is formed there is C2S. C2S is being formed in zone 2, and in zone 3, the C2S reacts with lime again to form the C3S. All right, and in the same zone 3, C3A reacts with lime, also react with the iron oxide to form C4AF. That's the calcium tetracalcium aluminoferrate. So in zone 4 here, actually there is some degree of cooling and crystallization of the various mineral phases formed. All these C3S, C2A, all these are minerals that are being formed in the kiln. So it is in zone 4 that they are being cooled and they get to crystallize. All right. Now, if you look at this picture, you'll get to see what the clinker looks like, the final product. So it is in step 4. You could see here cement mill, the clinker that has now been formed. Of course, it just behaves like a cement, but it is in the particular form. It is nodular and somehow circular. So in the cement mill, they are ground to a fine powder to turn the clinker into a useful cement. So this happens in the cement mill. So it's also in the cement mill you get to see they get to add some the gypsum to control certain time. A certain percentage is being added, and then it is now sent into a different storage, and then before it is bagged and then dispatched in box or in batches. Okay, so this is basically the flow chart for the manufacture of cement and the stages involved. And this is an overview of the whole process. You could see the raw materials for the manufacture of cement being fed into the kiln, and then all these compounds are formed. These are oxides that influence the cement properties, and then before gypsum is added and then ground to the finished cement. And then these compounds themselves, they are the minerals, right, with their oxide composition. This is the table we have just presented, their names with their chemical formula, their oxide composition, and the abbreviation. All right, so let us take a look at the chemical reaction of cement, one of which is called hydration. So when Portland cement is mixed with water, there are some chemical compounds. The chemical compounds present in it actually undergo a series of chemical reactions that causes the cement to harden And these chemical reactions with water is what we know as, is what we term hydration. So each one of these reactions occur at a different time and rate in the cement once the cement is mixed with water. So together, the results of these reactions determine how Portland cement hardens and gains strength. Now, hydration starts as soon as the cement and water are mixed, and the rate of hydration and the heat liberated, because it is an exothermic process. Okay, the heat liberated by the reaction of each compound is different, and each compound produces different products when it hydrates. Now, we could look at tricalcium silicate, which is C3S. The C3S actually hydrates and hardens rapidly and is largely responsible for initial set and the early strength of the cement. Okay, now Portland cement with higher percentages of C3S will exhibit higher early strength. Then the C3A tricalcium aluminate hydrates and hardens the quickest. So, and it liberates a large amount of heat almost immediately and contributes somehow to early strength. Now, gypsum is actually added to Portland cement to retard the C3A hydration. Okay, without gypsum being added, C3A hydration will cause the Portland cement to set almost immediately after the adding of water, and we don't want that. So the C2S, which is the dicalcium silicate, hydrates and hardens slowly and is largely responsible for strength increase beyond 1 week. Okay, then the C4AF, that's the tetracalcium aluminoferrite, hydrates rapidly but contributes very little to the strength. Use always allow lower kiln temperatures in Portland cement manufacturing, and most Portland cement color, the color are actually due to C4AF, the color effects that are present in the Portland cement. So they are due to C4AF, tetracalcium aluminoferrite. So we could actually look at the heat of hydration. All right, the reaction of cement with water is exothermic, as I've said earlier, and the reaction liberates a considerable quantity of heat. All right, and this liberation of heat is called heat of hydration, and it's actually clearly seen when a freshly mixed cement is put in a vacuum flask, and then the temperature of the mass is read at intervals. You could add this just more like a practical way of getting to investigate the heat of hydration. So the heat of hydration is generated mostly, and it is influenced actually by the proportion of C3S and C3A in the cement, and it's also influenced by the water cement ratio and fineness of the cement and the curing temperature. As each one of these factors I've stated increased, the heat of hydration actually increases. And the heat of hydration also depends on the chemical composition of the cement. And here you could see I've just tabulated the properties of the hydrated cement compounds. Okay, once they are hydrated, these are just the properties, and I've actually explained this, so this can serve for additional knowledge. So we could actually look at the physical properties of cement. One we will be considering here is fineness, the particle size distribution of the cement. Okay, it affects its reactivity and strength development, of course, increasing its surface area. Then we have density, that's the mass per unit volume of cement, and it's usually typically around 3.1 to 3.2 gram per cm cube. Then we have specific surface area, that's the total surface area of cement particles per unit mass. which also affects its reactivity. We have color. The cement can actually range from gray to white depending on its composition. Then we have odor. The cement has actually a distinct, slightly bitter or sour smell. Right? Solubility is one. It is insoluble in water but reacts with it to form a paste, which is actually employed in construction work. Then we have a certain time. This is actually the time it takes for cement to harden, ranging from few minutes to several hours. Another physical property is workability, the ease with which cement can be mixed, placed, and finished. So we also have a compressive strength, which is the ability of cement to withstand compressive forces. All right. And this compressive strength is measured in megapascal MPa or pounds per square inch, which is PSI. Then we have tensile strength. That's the ability of cement to withstand tensile forces, typically lower than compressive strength. Then we have a drying screen. Then we have a drying shrinkage. That's the amount of shrinkage that occurs as cement dries and hardens. We also have thermal conductivity, which is the ability of cement to conduct heat, which actually affects its behavior in various environments. And these physical properties of cement are actually important factors in determining its suitability for specific applications such as construction, masonry, and decorative work. And we could also have the various types of cement based on the percentages of the various constituents in the cement, such as the C3S, C2S, C3A, and all of that. So based on that, you could see from this table the different types of cement. We have the type 1, type 2. The type 1 are general purpose cement. Type 2 are moderately sulfate resistant cement. We have the type 3 high LE, type 4 are low heat of hydration cement, and type 5 are high sulfate resistant cement. So now let's look at the structure of cement. Actually, the structure of cement is characterized by a crystalline one. It's a crystalline structure with C3S and C2S forming a solid solution. And it's a porous and amorphous structure with C3A and C4AF forming a gel-like phase. And it's also characterized by a hydrated structure with water molecules bound to the cement particles.